Okay. Synthesis reactions are also called combination reactions. That's where, generally speaking, you're going to take a couple of simple things and combine them to make one that is more complicated. Okay? Synthesis reactions typically are going to release energy, usually in the amount of heat, sometimes light. That means synthesis reactions are exothermic. You should know that. Okay. Sometimes synthesis reactions need a little bit of startup energy to overcome the activation energy. Let's take a look at the next page. Let's go over a couple of really basic synthesis reactions. Here we have barium combining with chlorine to make barium chloride. If you're predicting the name of the product that's formed, I highly recommend writing it in words first, then write out the ions so that you can predict what the chemical formula would be of the product. Do not rely on looking at the subscripts on the reactants to predict the subscripts on the products. It is simply coincidental that it works out here that they are the same. Okay? If you're doing this next example, which is tin plus oxygen, and you're forming tin oxide. Tin is a transition metal. We usually don't know what the Roman numeral would be or the charge would be unless you could calculate it somehow or somebody told you. In this type of an example, you assume that it is a +2 charge when you go to put it in a formula, okay? So that means you would have SN +2, O -2, you would get SNO. Notice that you could not have looked at the subscripts on the reactants to have accurately predicted the subscripts that would have been on the products, okay? Okay, now, some common reactions that involve things that come together to produce one product, they're all outlined in a table on the next page. So I'll point them out to you within the reading, but I think the table is a lot easier to reference. Okay, so here when you've got a non-metal oxide combining with water, the product is always an acid. This example would be down here. SO3 is a non-metal oxide. You're forming sulfuric acid. You wouldn't necessarily know what acid you're forming, but I would definitely memorize this general equation, okay? Another thing that I would take a look at is metal oxides react with water to form bases, okay? So that example would be right here. And then last one would be when a metal oxide reacts with a non-metal oxide, the product is a ternary salt, meaning you're going to have 3 different substances in the salt. And that example is just underneath this one where you're forming the calcium carbonate. Okay. These reactions that I just talked about, the reverse is under the decomposition section. Okay, so if you memorize one direction, then you automatically know what the other direction is. So let's come down here. Let's talk about decomposition reactions briefly. So decomposition reactions are when you have one like complicated reactant and it splits up into more simple things. Since this is the opposite of a synthesis reaction, most decomposition reactions will actually require energy to get them to go. So since this is absorbing more energy to break bonds and it's releasing when they form, this would be an endothermic process. I think that's all I need to say about that. Okay, let's take a look at the next page. On the next page, they have showed you at the top. These are the reverse of the reactions that I showed you in the synthesis section. So you've got acids decomposing to form water and a non-metal oxide, bases decomposing to form a metal oxide and water, salt decomposing to form an oxide of metal and a non-metal. All of these examples are here. Here's the acid decomposition, the base, and the salt decomposition, okay? All of these reactions are outlined in this table, okay? So I would just know the table for sure, okay? Now, combustion reactions. Combustion reactions are going to have a hydrocarbon or a carbohydrate. The only difference is that the carbohydrate is going to have an oxygen in it, combining with oxygen to produce carbon dioxide gas and water. So you've got your hydrocarbon plus O2 producing CO2 and water, and you can interchange the hydrocarbon with a carbohydrate. Typically, you're given the hydrocarbon. So for instance, here is a hydrocarbon, C8H18. This is octane. It's in gasoline. It provides a lot of energy to move your car. This is also going to release a bunch of heat. So that means that combustion reactions are exothermic. Sometimes they're going to release sound and even light. An example of a carbohydrate undergoing combustion would be down here. This is glucose. Okay. Let's take a look at the next page. Let's go to single replacement reactions, okay? Single replacement reactions, here. Okay, single replacement reactions are also called single displacement reactions. Usually they abbreviate these as SR or SD, okay? So you're going to have an element, like let's say it's element A, combining with compound BC. They switch places, you kick one of them out, and you make a different compound. Technically, there are 3 different types of single replacement reactions: metal replacement, hydrogen replacement, and non-metal. So let me go over these briefly. Potassium is a metal, okay? Therefore, it would replace the metal in the compound if potassium is more active than copper on the activity series on the next page, okay? For the next one, here I have sodium metal. There are a few, if you have a highlighter, there are 4 metals in the activity series on the next page that will react with water at room temperature. You should highlight the first 4 metals on the top left: lithium, potassium, calcium, and sodium. I would just memorize them if I were you, okay? So lithium, sodium, potassium, and calcium, right? Okay. And these, you put them into water at room temp, it will react. So that means that the sodium will trade places with that hydrogen and water when you write water as HOH. And so that means that you'll form sodium hydroxide, which is a base, and you'll kick out hydrogen gas. So you'll see little tiny bubbles. You put any other metal in water at room temperature, it won't react, okay? The next one is non-metal replacement. Bromine is a non-metal. It's specifically a halogen. If it is higher on the list than the other non-metal that is in the compound, then this will react, and you're looking at the halogens on the right-hand side of the activity series on the next page, okay? So let's take a look at some practice problems. I need to point out a couple of things too also on this activity series before we go on. I just don't want to assume that you know all of it. So the metals are on the left. The halogens or the non-metals are on the right-hand side. The higher you are on the list, the more active you are. You will replace anything underneath it. You should highlight the hydrogen, and you should make a note that this would be what you use if you're putting a metal into acid. So that means any of the metals that are above hydrogen, when they are put into an acid, they will react, okay? I think that's about it. Yeah. Let's take a look at the quick check, and let's do number, I don't know, number 4 maybe, okay? So for number 4, this is calcium metal, and we're putting it into water. Is it one of the metals that will react with water at room temperature?
Yes.
Yes. So therefore, calcium will trade places with this first hydrogen. What I recommend you do is write this out in words. So this is calcium plus hydrogen hydroxide. The calcium and the hydrogen will switch places. You're going to form calcium hydroxide and hydrogen. Okay, so calcium, we already have that. And then we have the water. Calcium hydroxide is Ca plus 2, OH minus 1. You have to put parentheses around the hydroxide because you need to write more than one of them. Hydrogen is diatomic, so you would write H2. This is not balanced. You would need a 2 in front of the HOH to balance it, okay? If for some reason, let's say we're looking at number 2, okay? We've got copper and potassium. The question you want to ask yourself is Cu higher on the activity series than K? It's always the one that's alone. That one needs to be higher than the one in the chemical formula. Okay. So is copper higher than potassium? No. No. So that means this would be no reaction. You don't do anything but write no reaction. You're done. Okay. We good on that? Okay, now let's talk about double replacement reactions. Before I do that, I don't know if we'll see if I have enough time before this video ends. Let's go right here. Okay, double replacement reactions are where you have two compounds. The cations switch places, and you'll form two new compounds, okay? There are three categories of double replacement reactions. There's precipitation, neutralization, and gas formation, okay? Precipitation will produce a precipitate, okay? So an example of a precipitation is down here. Here is my precipitate. This is my insoluble product, okay? Neutralization is when you have an acid combining with a base to produce salt and water. Neutralization reactions are exothermic. They will feel warmer if you're holding that container, okay? Then we have gas formation. So gas formation for you could result in forming a couple of compounds that are really unstable. So here it says a few products of double replacement reactions are not very stable, so they spontaneously decompose and they form water and a gas. The two most common are carbonic acid. Carbonic acid is H2CO3. If you ever produce that as a product, you can't write it like that. You have to write it as H2O and CO2 gas. Okay, the other one is ammonium hydroxide. So if you form NH4OH, you can't write it like that. You have to write it as ammonia gas, which is NH3 plus water, which is H2O. Does that make sense? Okay, they gave you a couple of examples here. This reaction produced carbonic acid. They didn't show it that way. Okay, this reaction formed ammonium hydroxide. Notice they didn't show it that way. Okay. Okay. If you ever produce ammonia gas, it stinks. It has a really foul odor. I would know that if I were you. And then if you add a base, then just read this part, okay? Note this. If carbon dioxide gas is produced after you add an acid, like here, this is an acid. Here's your carbon dioxide gas. So that means that is evidence that the carbonate anion is present. And then for the other